Welcome to the Machines and Mechanisms mini project. So this is the problem definition for our problem. We're analyzing a pendulum system made of rigid pipe attached to a massless rod rotating about a fixed pivot. Goal is to derive expressions for angular motion, reaction forces, and ultimately tension, and validate them using a MATLAB simulation. This is a list of the relevant parameters that we'll be taking into consideration when we are solving for our variables of interest. So we have our angle, length, angular acceleration, angular velocity, radius of pipe, and the mass. These are our principles. The key principle that we will be using is Newton's second law of motion, relating forces to mass and acceleration of a body. The components of rotation, acceleration, conservation of energy, and finally, a given formula for mass moment of inertia to accurately calculate for a hollow cylinder. Here we have our free body diagram. We drew the free body diagram showing all the forces, the weight, the reaction forces, the angular motion. We identified the tangential and normal components of the center of mass of acceleration, which are used in both force and moment equations.
We apply Newton's second law for moment and forces in the x and y directions as starting points for alpha, rx, and ry. By substituting the equations for rx and ry in the moment equation, we can eliminate these two variables and solve for angular acceleration as shown. Using the angular acceleration expression, we substitute back into our original force equations to isolate the horizontal and vertical reaction forces completely. We apply energy conservation to find angular velocity based on the height difference between the release angle and the current angle. This gives us a general expression for angular velocity throughout the swing. At the lowest point in the swing, where angular velocity is maximum, we calculate the total tension. This includes both the static weight and the dynamic centripetal force. We've implemented all equations in MATLAB and Simulink using these various parameters. At 10 degrees, the simulation matched our theoretical values for acceleration, velocity, reaction forces, and tension. At the lowest point of the swing, the simulated maximum tension was nearly identical to our calculated value, confirming our model. This validates both our physical modeling and simulation approach. Newton's laws and energy conservation gave us full control over the dynamics, and MATLAB verified our predictions with high accuracy.